Morning, everybody. I just wanted to film a short, well, it's not gonna be short, but two videos finishing up the Unit 1 packet because looking at the future couple weeks, we only really have about 13 more days until my interim trip leaves. Very short. We're about 3 weeks away from that. And now that we've completed kind of our Unit 1 summative, there's about 2 different topics that I want to make sure you had some resources on that you could finish this off, spend iLearning today essentially taking a look at it, or looking at it at your own pace. Because some of the examples are a little bit technical, and so I'm going to kind of split this into 2 videos, 2 parts. One, finishing up our limits at infinity, starting with example 4, which is on page 38 in your notes. And then the second video I'm going to make concerning the last lesson, which is 1.9, which will be much shorter. It's a really, really important theorem, and so I want to make sure we talk about it because there will be some questions that pop up as we kind of continue into the next couple of units that are built off of it, but it's not really enough content, I think, to spend one more day on, and this way you can kind of learn on it on your own and still wanted to provide you some teacher support. So if you take a look at example 4 in your packet, this is on page 38, I believe it's 1.8, limits at infinity. What we were talking about in this lesson were limits at infinity, so limit as x approaches positive or negative infinity. So just doing the plus or minus here to make it one limit expression, so having the right 2. And when we solve this, if we get an answer to this, these limits at infinity, what we're uncovering are the horizontal asymptotes for our function, in this case f. We're seeing that a function trends to a constant, whether that's 0 being the x-axis or another scalar number, either positive or negative. But when we solve these limits, if I get a number answer, what we've essentially discovered is the horizontal asymptote. My function will start to approach that. It will start to behave linear once we go out far enough in either direction. And there's a really not special type of problem, but there's two types of functions where, notice the plus or minus can typically go down to one answer. Therefore, there's one horizontal asymptote. There are some functions that have 2. We actually looked at one of those in class and talked about it, which was arctan. Arctan has 2 different horizontal asymptotes. If x is going to go off to infinity, then this limit is equal to pi over 2. But if I want to take the limit of arctan and let x approach negative infinity, then this answer is negative pi over 2. And so it's this connection to whether I'm going to positive or negative, how the answer is positive or negative. Now, in theory, this is really connected to tangent and how those are my vertical asymptotes. So when I do an inverse, we're putting them on their side. And because of the graph, we're seeing these 2 different behaviors. But notice that there's kind of a correlation in the signage and how things are traveling. And this is one specific type of function that's not a piecewise function, but has the property or the characteristic that there are 2 horizontal asymptotes. There's not a single number that we go to. There's actually 2 answers. And there's one other type of function, and this was that special function I was referring to, and it deals with square roots. And ultimately what we'll kind of talk about is it's really any even root this can happen to. So a 4th root, a 6th root, an 8th root, but you typically don't go that high. But majority of the time, specifically in an AB calculus, so Cal 1, just a square root is typically what you would see. And before I can really show you the example, you need kind of a key thing from Algebra 2 that's just not as defined anymore, which is another reason why I wanted to kind of give you this opportunity or this video to kind of talk about it. And it deals with the expression square root of x squared. And a lot of y'all hopefully would want to gut check and immediately go through and say, well, the square root and the square are inverses, so this answer is just x. So like if I was to go through and take the square root of something like 4 squared, this answer would just be 4. if I was to go through and take the square root of negative 4 squared, you would want to say the answer is just 4, because negative 4 squared is 16, square root of 16 is 4. But in actuality, that's not really the answer, and it's because of, again, how the square root and the square are acting. This answer was 4 because these two things canceled, not because I simplified it all out. Because notice what happens is that when I simplify this out, when I square the negative 4, we lose the negative sign. I lose the fact that this was a negative 4 to begin with. And it can be confused as if we used 4 from the beginning. And so what we need to do is kind of think about this and define it a little bit more specifically, where if these things are going to cancel, the answer is negative 4. The answer is the input. And what that's kind of describing now is this relationship that if I square root x squared, I'm going to use parentheses specifically, this answer comes out to be x. But if I square root negative x squared, this answer should be negative x. Or if x is positive, we're going to take the positive x answer. If x is negative, then we're going to take the negative x answer. And what I hope this rings a bell with is this is the exact same scenario as absolute value of x. That we defined this as a piecewise. Absolute value of x is equal to x if x is positive, if it's greater than or equal to 0. Absolute value of x is equal to negative x if x is less than 0, if x is negative. And that's what we have here. So when I'm simplifying this expression, it's not just equal to x, and it's not just equal to negative x, it's equal to both, because it depends on what x's are we using. In this case being absolute value of x specifically. And if you remember when we were looking at this limit in some previous lessons, what x was approaching really mattered for the absolute value because we're looking at two different pieces. If x is going to infinity, then we're looking at the positive x. If x is going to negative infinity, we're looking at negative x. We have to pay close attention to the pieces that we're focusing on and the pieces that we're trying to take the limit of. So right now, what I want you to remember is that when I'm taking the square root of x squared, that's equal to absolute value of x, which is equal to this definition. It's x if x is greater than or equal to 0. It's negative x if x is less than 0. In other words, if this is a positive value, then I'm going to get the positive answer. If this is a negative value, I'm going to get the negative answer. Keep that in mind for when we're asking the question in example 4, which is to find the horizontal asymptotes of this rational function. And you'll notice how this rational function deals with square roots. So, let me get this erased. And let me put this example up. So I have the function rational, up top the square root of 2x squared plus 1, and then underneath I have 3x minus 5. And the question is asking for the horizontal asymptotes. And what you need to remember in terms of context is that when you see a problem asked for the horizontal asymptotes, we are looking for the limits at infinity. I want to let x go to infinity for this function, and I want x to go to negative infinity for this function, and I want to see, do I get an answer? If I get an answer, those are my horizontal asymptotes. So I want to take the limit of this going to positive infinity, and I want to take the limit of this and let x go to negative infinity. So I'm going to write that here. Limit as x goes to infinity, I'm going to rewrite the problem, 2x squared plus 1, underneath 3x minus 5. Now let's just focus on the positive version right now. Because when we're doing specifically the limits at infinity, recall that we're focusing on dominant terms. Once x gets large enough, specifically look in the denominator, that minus 5 becomes insignificant. We showed and verified that that will essentially go to 0. I'm essentially going to be subtracting off nothing because this 3x is going to dominate the entire problem. In other words, this limit underneath will go to 3x. That's my dominant term. But because I have the square root on top, we haven't seen anything like that. If there was no square root, then my dominant term would just be 2x squared, and we could go through and complete the problem as we've seen with just regular rational functions earlier. With the square root, it's very intuitive to say, oh, well, that's still the dominant term on the inside. I just include the square root, and you're not wrong. what we're actually going to do is take the square root with it, but take the dominant term from up top. Like, that's the technique. And when I'm looking at this, I've got the square root of 2 times x squared. That's really root 2 times root x squared. And hopefully now what you're kind of seeing is why we even talked about the piece that we talked about before. That, and I'm going to grab a different color. Right here, I have the square root of x squared. And remember that depending on what x values that we're traveling on, this can be equal to one of 2 different things. Now, because we're letting x go to positive infinity, then x is greater than 0. Well, this is equal to the absolute value of x. And if x is greater than 0, then this is just x. My dominant terms essentially will simplify into root 2 times x over 3x. Notice how the dominant terms are the same. These x's cancel, and I'm left with root 2 over 3, and there's my number. That's my horizontal asymptote. But that's the horizontal asymptote for when x is going to infinity. If I want to let x go to negative infinity, we're doing the exact same thing, where I'm going to go through same function, taking my dominant terms. So this is essentially going to take me to root 2x squared over 3x, or root 2 times root x squared. But now we have to be really careful, because if x is going to negative infinity, x is now less than 0. Well, if this is absolute value of x, when x is less than 0, this is equal to negative x. So now I've got root 2 times negative x over 3x. And notice the x's will still cancel, but notice how my answer is negative. And so what this creates then is 2 horizontal asymptotes. And algebraically, this is how we show that. It occurs because of the square root in the x squared. When a square root in x squared, if x is going to infinity, we get a positive answer. When x is going to a negative infinity, we get a negative answer. As long as underneath we still have that x, because that's what's canceling out the x's overall. So, in previous problems, we could just compare the degrees. The fact that this was squared over 1, if this square root wasn't here, there would be no horizontal asymptote. But because we're taking a square root, this is really worth just x. They actually have the same degree. We just have to be very, very careful about where my limit's going. And again, AP style questions, you may see this once, you may see this twice. It's a harder type problem, but it's one that you see enough, or I needed to show you, and that you would have some video practice on. I'm going to leave example 5 for you to try. You'll notice in example 5, you have the square root of 9x to the 4th. Well, that's 3x squared if you were to take the square root. Well, you're square rooting x to the 4th. There's still the positive and negative infinity. Right? It's the square root piece. But notice that the degrees would match between top and bottom. So try example 5, graph these in Desmos. You should see that your graph has 2 horizontal asymptotes. Depending on which direction you're going, you should be able to find what those values are algebraically. So you should be able to check. So use Desmos and check that. But example 4 is there for you to try. I'm going to skip example 6. I'm going to let you take a look at that one on your own, as well as take a look at example 7 and example 8, because we talked about those. So that kind of rounds out our first part. It's really just going to kind of show you the one example, and then if you have more questions, let me know, and I'd be more than happy to work with you outside of class during tutorials. So.